All right, I guess it's time to start. It's my pleasure to welcome everyone to the Oxford Set Theory seminar. And for the record, we're recording this. The video will be made available a bit later on. So today's speaker is Ali Enayat, who I've known for many years, and it's really great to have him here talking to us. He's going to be speaking on the topic of Leibnizian and anti-Leibnizian motifs in set theory. Ali, how would you like to handle questions? Should people raise their hand electronically or interject, or how do you want to do it?
I think it would be perfectly fine for me to be interrupted, but I will be concentrating on the slides. So if you don't mind monitoring maybe the any chat suggestions for questions or hands going up, and I'll be glad to answer any questions along the way.
Okay, so with that, then why don't you go ahead? I think I have to make a setting so you can share, or can you share already?
No, I couldn't share yet.
Okay, so I think you should be able to now. So
yes, now I could do it, yeah.
Okay, so please go ahead, Ali.
Okay, very good. So I think you can see my first page, yes?
Yes.
Very good. So I'll be reporting on work that dates back, work of myself basically, that dates back from about 2004, since when I started getting interested in questions about Leibnizian themes in set theory. And then not long afterwards, I realized that there are also anti-Leibnizian ideas that one can explore. And given the fact that we're talking about 2020 right now, one can say I've been working off and on and mostly off on this topic. But the span of the results actually does extend to work that I'm actually writing up right now. So this is a rather mix of old and new results. Okay. We will start now with just the basics, just to be reminded of Leibniz's principle of identity of indiscernibles. It dates back to a particular work by Leibniz, where one hears that there's Leibniz's dictum that no two distinct substances exactly resemble each other. Well, there are various ways of interpreting this dictum. One plausible way to read this, especially if one has exposure to model theory, is that it's saying something about objects and properties. And objects can be modeled by points in a structure, properties by formulas that are true or false of a particular object. So we come to the model theoretic interpretation. If you give me a model in a language L, and I'll be finicky and distinguishing between the structure M and the universal discourse of it, then we let the objects refer to the elements of M and the properties to refer to those that are L expressible via first order formulas with one free variable. Now, with this reading, one can say that a model is Leibnizian if you fix your model and your language, if it doesn't contain any pair of indiscernibles. In other words, if you give me two distinct elements A and B, there should be some formula in the language with one free variable which helps to distinguish them from each other. Phi of A holds and P of B is false. Okay, so in the language of model theory, this basically can be reformulated in the language of types, that if you look at the each element and compute its type, then it would be unique to that element. Any two elements would have distinct types. But the definition you're seeing is perfectly fine and says exactly what I just said in a simpler way. Now, in terms of examples, as you see, the name of this particular page is familiar examples. As soon as you have a pointwise definable model, then you have a Leibnizian feature. By a pointwise definable model, I mean a model such that if you go to each element there's a formula with one free variable that only that element and no other element satisfies. So it's very easy to see that any point-wise definable model is Leibnizian. So this gives you a nice supply. For example, if you just look at a set of natural numbers with its usual order or any expansion of that, or if you look at V omega, this is the omega-th level of the von Neumann hierarchy. You have this point-wise definability. If you want a fancier example, one that is dear to us set theorists, is the Shepardson-Cohen minimal model of set theory. It's the first L delta, such that you have a model of ZF. In general, point-wise definable models of set theory can be easily found as for a particular theory if your theory extends V equals to hot. So this particular model, the Shepardson-Cohen minimal model, has no large cardinals or has very, very specific features, but if you have V equals to hot in your theory, then that theory will have a point-wise definable model. Okay. Now, the family of Leibnizian models, if you think of them as a family of models, is sandwiched strictly between the family of point-wise definable models and the family of rigid models. Now, by rigid, I mean a model which has no non-trivial automorphism. It's easy to see that if a model is Leibnizian, then, and if you have an automorphism, then any elements that you pick, an automorphism would only take it to itself because automorphisms preserve types. The example here of strictness is easy to see because there are lots of rigid models that are not Leibnizian, because you could find rigid models of arbitrary size, but Leibnizian models have a premium on their cardinality. If your language is countable, then their size is at most continual. Now, in terms of examples of Leibnizian models that are not point-wise definable, I haven't given you any on this page yet. So the most familiar example would be the field of real numbers. If you give me any two distinct real numbers, then there's a rational in between them, and rationals are expressible first order-wise in the language of fields. So you can tell them apart by that rational that sits between them. With a similar argument, and even easier, you could show that the omega plus 1th level of a von Neumann hierarchy is Leibnizian. And of course, it's not point-wise definable because it's too large. Any point-wise definable model in a countable language must be countable, and this is of size continuum. Now, in terms of algebraic examples, every Archimedean ordered field is Leibnizian, with the same reasoning that the field of reals is Leibnizian. So there is nothing new here, just generalizes that example. But if you stick to real closed fields, then the only Leibnizian real closed fields are the Archimedean ones, using Tarski's elimination of quantifiers. This is pretty much the last page that is about generality. So one might wonder, looking at this example, if there are larger Leibnizian models of ordered fields. And there was a fantastic theorem, well, two fantastic theorems you can glue together, and yet non-Archimedean ordered fields that are Leibnizian and they're large, of size continuum. And what I have in mind is a construction of Geithman. This has to do with models of arithmetic, and in particular what are known as minimal end extension types. That allows one to build a model of PA. For any completion of PA, you can build a model of PA of size continuum that is Leibnizian and of size continuum. Now, if you look at the rationals of that model, then the rationals of that model will be bi-interpretable with the model thanks to the theorem known as Matiasevich-Robinson-Davis-Putnam theorem. So one can glue these two together to get big Leibnizian non-Archimedean ordered fields, and in particular models of PA. And now, since we're in the domain of set theory, we're in a set theory seminar, let's look at Leibnizian models of set theory. So the bad news is that a simple compactness theorem, or if you want a big machinery, the Ehrenfeld-Mostovsky theorem about indiscernibles, quickly gives you the fact that if your theory has an infinite model, then it has a model that is not Leibnizian. So overtly, we cannot enforce being Leibnizian by a first order condition. That's the bad news. And this must have been a block to many people trying to formulate a first order version of Leibniz's principle. And it is a serious block. On the other hand, back in 1995, in a paper in the Journal of Symbolic Logic, Jan Michalski introduced an axiom that captures the spirit of Leibniz's dictum in a sense I'll explain on this page. In the sense that once you see this, the theorem that he proved, you'll see why it's capturing the Leibniz's principle of identity of indiscernibles. Now, the first order axiom, he didn't call it LM. I've been referring to it as Leibniz-Michalski, therefore LM, since back when I started working on this. So that's why you're going to be hearing LM as a name for this axiom. Let me emphasize, it's a statement in set theory. Overtly, it might not appear that way, but here's the statement. Let's look at it. It says if you pick any two objects, X and Y, in the universe, as long as they're different, you can find an ordinal which is high enough to contain both of them. And if you compute the first order theory of V alpha with epsilon and the constant for X and that for Y, then these two first order theories are different. Now, this sentence about first order theories is expressible in set theory because within set theory we can compute first order theories of any set structures. So despite its apparent lack of expressibility in first order logic, within set theory this is expressible. Now, the theorem that in a way clinches this axiom as doing the job was proved by Michalski back in that paper, and it was then generalized in a later paper of mine in 2004. I wrote a paper called Leibnizian Models of Set Theory in Journal of Symbolic Logic. So part A says, so the theorem is about complete extension of ZF, and there are three conditions that are equivalent. A and B are due to Michalski, A and B being equivalent. So T has a Leibnizian model if and only if T proves this axiom LM that you're seeing over here. And then the fine tuning that I added was that you could build continuum many countable non-isomorphic Leibnizian models of T. And one of the reasons I was interested in this result was that the proof of Michalski overtly didn't seem to give you many Leibnizian models, and I was trying to find mechanisms of producing them, various ways of producing them, which are versatile. So I'll give you the tools that are needed for this theorem. Once you have these tools, it's pretty easy to prove the equivalence of A, B, and C. So the first result that is the one that Michalski used in part of half of his theorem is that every completion of ZF has a model, each of whose ordinals are pointwise definable. I wrote a paper on this class of models and proposed that they be called Paris models in 2005. And so I'm going to be referring to them as Paris models. This theorem is proved using the omitting types theorem. It gives you one, okay, overtly. Now, the other theorem is the so-called extended reflection theorem of Myhill and Scott. It's a nice embellishment of the ordinary reflection theorem of ZF. And it's a kind of theorem I think that every set theory student should know at some point, maybe even as an exercise, once they've seen the ordinary theorem. That ZF proves that if you give me an ordinal and any formula, so the formula is given in the meta theory, the ordinal is given in the theory, then there's a CUB closed unbounded class of ordinals gamma such that that ordinal that you specified is first order definable in V gamma, and V gamma reflects phi. Any property expressible by phi is absolute between the universe and this truncation of the universe given by V gamma. So they proved this theorem directly by just embellishing the proof of the reflection theorem. But it turns out if you take the ordinary reflection theorem and you hook it together with Paris's theorem, then you can get this for free. So that's also a nice exercise to work out. So it turns out to be able to mass produce Leibnizian models, the argument that I gave distinguishes the two cases that T proves that V is equal to Hod and V is not equal to Hod. So V equals to Hod is a first order statement that expresses that every set is ordinal definable. It's a statement that was introduced by Gödel in an unpublished paper, but in a talk. The details were worked out by Michael and Scott, and apparently it was also independently discovered by Fopenka. So if you have a completion of ZF that proves V is not equal to Hod, then there continue many countable non-isomorphic Paris models, each of whose ordinals are pointwise definable. Now, the way I proved this theorem was to use the omitting types theorem over and over and over, and the assumption that V is not equal to Hod to show that there are Aleph 1 many at least countable non-isomorphic Paris models. And then well, with usual coding techniques, you could show that the family of countable Paris models that are non-isomorphic, they form a analytic subset of the inappropriate Polish space. So by the fact that such subsets, as soon as they're uncountable, they have size continuum, is how I got this theorem. So some external set theory plus some internal set theory. Now, in the case that V is equal to Hod, then another theorem which helped was in a paper in Fundamental Mathematical called Counting Models of Set Theory, where I showed that if you have a model of Hod and it's countable, then there are continuum many non-isomorphic minimal elementary end extensions. Now, an end extension is an extension whose new elements come on the top of, in the sense of rank, of the old elements. A minimal elementary end extension is an elementary extension of a model such that between the first model and the extension, there is no proper elementary submodel. So if you have a Ramsey ultrafilter and take it ultra power of the universe, you get a minimal elementary extension of the universe, but not an end extension. Of course, as you see, the model here is countable, so we're in a different setting. So let's see. Then to hook these together, basically with Leibnizian property, is this theorem. Every minimal elementary end extension of a Paris model of V equals to Hod, ZF plus V equals to Hod, is Leibnizian. So this gives you a way of mass producing Leibnizian models. In the sense that you build a lot of Paris models, and then you build a lot of Leibnizian elementary end extensions if V is equal to Hod. And if V is not equal to Hod, then the Paris models themselves can be used to show that that there are lots of Leibnizian models. This last theorem is based on a
Ali, can I ask a question before you
of course. Yeah.
go back to that slide? So can you remark on whether you're adding new ordinals? I mean, for end extension, sometimes people are confused between end extension and top extension and so on. And
thank you. Yes.
So if you could just address.
Yes. Thank you for asking that question. So in general, an end extension is not a rank extension for models of set theory, because an end extension simply says that no old element gets a new member. But if you have elementarity, an elementary end extension of a model of ZF using the V alpha hierarchy, one can easily show that it becomes like an ice cream picture, that it's a rank extension. So a minimal elementary end extension will add new elements on the top of the old elements. And therefore it's a top extension in the language of top, yeah. Any other questions? Okay. So I just wanted to give you a flavor of a lemma that is used here. It goes back to Ehrenfeucht for models of PA, and the analog of it happens to work for set theory because even though set theory and PA are very different, they both think of their universe as being well-founded, and that's what kicks in here. If you start with the model of ZF and you pick two ordinals, such that alpha is larger than beta, and if you have a term, a parameter-free term, that gives you beta when you plug in alpha. So think of it as beta is definable from alpha without parameters. Then alpha and beta are discernible in M. And the proof is a delight. It really goes back to Ehrenfeucht's idea. Starting with the assumption that you have such a tau acting on alpha and beta that is shooting alpha down to beta. We define a class function assigning to each ordinal theta a natural number which measures the longest decreasing sequence of iterates of tau starting with theta. More precisely, f of theta is equal to n if you can build such a chain, but the next step, either tau of n plus 1 of theta is undefined or it's not an ordinal. It doesn't, it basically stops there. By 1, f of alpha and f of beta have different parities. And therefore you can distinguish alpha from beta by basically seeing which one has the property that f of alpha is even. There's a nice paper by Joel and Vika Gitman and Fuchs. I forgot his first name. Could you remind me, Joe?
That's Günter Fuchs.
Günter, thank you, yeah. That explores Ehrenfeucht's lemma in the context of set theory. And so there's actually lots to be said about this phenomenon in set theory. If I remember correctly, it's in the Notre Dame Journal of Formal Logic. Okay. Now, what about uncountable Leibnizian models of set theory? Because everything I've said so far is about countable ones. So it turns out if you have a model of ZF plus V equals to hot and you pinpoint any regular uncountable cardinal, for example, Aleph1 or your favorite uncountable cardinal, then one can build lots of models that are Aleph1-like, that are elementary extending M, and are Leibnizian. Now, Aleph1-like means the class of ordinals of the model has size Aleph1, but each proper initial segment of the class of ordinals is countable. These models have the nice feature that they don't add any new elements below kappa. So if your kappa was, for example, omega 1, and your model that you began with was an omega model with no non-standard natural numbers, then these Leibnizian models would also have the same feature. So they perturb the part of the universe that are above kappa, and they otherwise don't perturb what's below kappa. I don't know how to build uncountable models that are Leibnizian that only satisfy V equals to, LM, Leibniz-Michalski principle. We'll come back to the Leibniz-Michalski principle in a few seconds. So I'm sticking to the stronger statement V equals to OD to get the job done. And then it turns out another tool to build large Leibnizian models of set theory is gotten by this notion of being a super minimal elementary extension. A super minimal elementary extension is like a minimal elementary extension, but it's being super has to do with the fact that if you pick any element that is new and any element that is old, then this new element can define the old element via some formula. So you can, if you want a picture, just imagine an ice cream cone. It doesn't say elementary end extension, but these can be arranged to be an elementary end extension. Imagine an ice cream cone where the new elements are in the ice cream part, and the idea is that if you pick any point in the ice cream, you can define any element within the cone, which is rather remarkable that you could do this. So these were built for models of arithmetic by Raman Kasak and Jim Schmerl in their book. And it turns out one can adapt the construction to models of V equals to HOD to construct them. So every cannibal model of ZF plus V equals to HOD has such a superminimal elementary end extension.
Wait, sorry, Ali,
Oh, of course.
what do you mean by parameter-free definable from an element? I mean, if you're defining it from an element, isn't that the parameter?
Right. So basically, no other parameter besides the element that you picked.
Oh, okay, great, thank you.
Yeah. So if you iterate these superminimal elementary, this theorem that you see, this one, the fact that there are superminimal elementary end extensions, if you iterate this L(1) times, then using the Ehrenfeld lemma, you could verify that what you have is a Leibnizian model, and you can do enough variation along the way to build 2 to the L(1) many of them. So maximal number one can hope. Now, just as a final remark on this page, there's the powerful theorem of Geithman that I'm mentioning here is the one that I mentioned earlier in connection with the Matiasevich, Robinson, Davis-Putnam theorem about minimal end extension types. One can build Leibnizian models of ZFC plus V equals to OD of size continuum. Notice everything on this page before this remark is of size L(1). But these models have a feature that they're omega non-standard. So if you want omega omega standard, or at least even higher level of standardness, then this Geithman theorem is of little help, but you can adapt it to omega standard models if your model has a weakly compact cardinal. Okay. Now we come back to LM. So we just saw LM briefly, and then we just saw that it captures the spirit of Leibniz's principle, and then we didn't see it again. Now we get to explore it as a principle in set theory. What kind of relation does it have with other set theoretical statements? How does it sit in quote unquote ordinary set theory? So I want to begin with a particular set of selection principles, which goes back to the work of Kinna and Wagner in 1955. They formulated these 2 principles. The first one, KW1, is that if you have a family, for any family of sets, there's a function f. So this function f is going to be like a choice function, except that instead of going and picking an element from each member of this family, it goes and breaks it in 2. If a set, here's the statement, if you have a set A in script A in your family, and the size of it is at least 2, there are at least 2 elements in it, then your choice function picks a proper subset that is not empty. Hence the idea of ripping in 2 non-empty pieces. And then KW2 is that every set can be injected into the power set of some ordinal. If the power set here was just deleted and it was just some ordinal, this would be just the axiom of, it said every set can be well ordered. If you have a one-to-one map from a set into an ordinal, then you can use the function to well order the set. So this is a weakening of well orderability of every set. So in their paper, they showed that within ZF, these 2 principles are the same. And the argument is very reminiscent. If one has seen Zermelo's argument that a global choice function, let me retrace what I was going to say. Zermelo's theorem that if every set is well orderable, is equivalent to the axiom of choice, then just pretty much by having seen that proof, you can, if you sit down and work at it, you'll be able to prove this. There's a global version.
Could I ask a question about that?
Oh, yeah.
So the power set of an ordinal is even without any choice, is always linearly orderable. And so
precisely,
there's a very weak choice principle, which is about every set can be linearly ordered.
yes, exactly. That's
related to these principles at all, or?
Yeah.
I guess it implies that every set can be linearly ordered.
Exactly. Yes, and I don't remember who, but I know that is every set being linearly orderable is weaker than Kino-Wagner principle.
Okay.
Maybe Andreas would remember who or when this was proved.
I don't remember who was responsible for that, but I'm sure it's in Yek's book on the axiom of choice, probably as an exercise.
Yes, that's right. Yeah. I have it actually on my bookshelf, but it will take me a while to look it up. Okay.
I have it on my bookshelf too, but my bookshelf is at the office and I'm not.
Well, I'm seeing a bookshelf behind you, but I guess that's different books.
That has Yek on it.
Just like in the ordinary, in the ordinary setting of choice and well-orderability, one has a global version. You could have also a global version of Kino-Wagner principle, that there's a definable map that goes to any set which has at least two elements and picks a proper subset that is not empty. So here, this f of x should also say that it's not empty, just like KW1. Overtly, this doesn't look to be expressible in first order logic because basically this is something which could be true of a model of set theory, because you're saying there is some definable map somewhere of some complexity that does the job. But it turns out you could actually pin it down to a first order version, as you'll see in a second. Then there's a KW2 having a global version, that there is a definable map G, again without parameters, that injects the universe into the class of subsets of work. And the paper that I wrote back in 2004 on the Leibniz-Michalski principle shows that that actually these global versions of Kino-Wagner principle are equivalent to the Leibniz-Michalski principle. So Leibniz-Michalski principle now gets a new clothing. It's basically global Kino-Wagner. And since Leibniz-Michalski is expressible first order wise, this theorem also shows that these global KW principles are also expressible first order wise. Just as you eyeball this theorem, let me just vary it a little bit. Sorry about this part showing up. I want to remind everyone that it's well known that for a model of ZF, having a global choice function that is parameter-free definable is equivalent to V equals to HOD. So that theorem somehow is a global analog of Zermelo's theorem. And using ideas from that proof, one can sit down and prove this theorem. So this theorem uses some basic ideas. It could have been easily proved back in the 1950s, let's say, or 60s, whenever I guess 60s, by the time 55, Kino-Wagner was introduced. Okay, now going back to a question and that also comment that Joe made. Here's some concrete consequences of this equivalence. So first of all, you get Kino-Wagner from Leibniz-Michalski. So Leibniz-Michalski has concrete, familiar consequences. V equals to OD, which is the same thing as V equals to HOD, proves LM. So LM is a weaker form of HOD. In the presence of ZF plus LM, Leibniz-Michalski, there's a parameter-free definable global linear ordering of the universe, precisely based on Joel's observation that once you have every element tagged with a subset of ordinals, it's like tagging elements with transfinite 0-1 sequences, which can be linearly ordered. Then you use those tags to linearly order the universe. Now, the nice thing about that is that, therefore, you could have a global version of choice for finite collections of sets. If you give me finitely many sets, that linear order is going to be able to, for you to pick up the least element from each finite set. So LM does give you some nice trace of global choice. And this last one is a consequence of the previous one. For GC2, Sierpinski already proved that if you have a choice function for a class, if you have choice function for pairs already, by doing a finer version of the Hamel basis construction, you could define actually a set that is not Lebesgue measurable, that is subset of real numbers. So the idea of what you're seeing on this page is a connection between LM and familiar statements of set theory. Okay, and now some more powerful results, independence results, forcing results about LM. So it's not hard to show that there are models of ZFC in which LM fails. If you introduce the notation of bracket R as being also for a real R of those x's that finitely differ from R, then by a symmetry argument, you could show that if R and S are mutually cohen over the constructible universe, then you have this version of indiscernibility. Notice this version is actually stronger than just this discernibility a la Leibniz, because this says for any binary formula, you have also indiscernibility. I'll come back to this stronger form shortly after these slides.
Do you need L there, or?
The indiscernibility, let's see.
It's going to be some kind of
no,
forcing
probably not. You're
homogeneity
right.
argument, right?
Yeah, you're probably right. Yeah, because then, yeah, I think you're right. Yeah, I don't need L there. Yeah. Okay.
Sorry, could you do the same thing instead of with omega with your favorite definable cardinal kappa and kind of witness the failure of LM at any level that you like?
Oh, I'm pretty sure you can. Yes, those. Yeah, that's right. There's those kind of symmetry arguments works at high levels, and if I remember, not long ago, Joe worked them out to build a model of ZFC where V is not equal to HUD of any parameter by just adding lots of these indiscernibles along the way. Yeah.
Okay, thank you.
Yeah. And then in terms of classical models, LM fails, but the statement that there's a parameter P from which LM holds in the famous model of set theory due to Halpern and Levy. Well, the model was introduced by Cohen, but it was analyzed by Halpern and Levy, where they showed that Boolean prime ideal theorem and ZF hold, but not AC. So this parameter P is actually a family of reals in that model. And LM fails pretty much because there are Cohen reals in there. So there's a parametric version of LM basically that I didn't say something about, but I'm kind of tucking it in here. What about LM? And we saw that V equals to OD implies LM, but are these, can we build a model? So it turns out you have to work hard to get such a model. So the proof appears in the 2004 paper that I wrote, and it includes this theorem by Solovay. So he basically used Jensen's, I guess it's pronounced Jensen, CCC notion of forcing for adding a pi12 singleton of minimal constructibility degree. So this is a finer version of Sachs forcing, which can be constructed using diamond omega 1 the way one constructs Suslin trees using diamond omega 1. And then you let Q to be the poset that adds a countable sequence of such generics with finite support. And then L of G would be your desired model. So of course, these are proof outlines, but this just gives you the gist of what's involved. So this theorem, notice it says ZF, it doesn't say ZFC. So the consistency of ZFC plus LM and B is not equal to OD remains an open question. It would be interesting to answer that. It's been open. And another open question, both of these were posed in my paper, is whether you have a model of ZF even without choice, where the ordinal definable reals are only countably many. In all the models we have, they're uncountable. Okay, just this is the last page about LM. I had asked maybe we can build such a model by analyzing the Sachs extension of L back in 2004. But I asked this in an email to Solovay. Actually, no, I take it back. I even had a proof outline that it holds. So it wasn't really a question. It was, I suspect it holds, and this is the proof outline. And he said, no, the exact opposite is the case. Actually, if you add the Sachs real, then LM fails. And it actually fails in a very dramatic way. So Solovay communicated this fact, but not the proof to me back in 2004. And it basically remains unknown exactly how did Solovay's proof go. In a recent paper with Conove, a proof of this fact is given, and it's been fine-tuned to what you're seeing in part B, that there's a pi12 partition of non-constructible reals into two non-empty sets A and B, such that neither cell is OD. Just think about it. There is a nicely definable pair of families of reals, and this is actually a partition of non-constructible reals, such that this partition is OD, but neither cell is OD. That quickly shows that A and B are indiscernible, because if they were discernible, then you could actually define both cells. They're indiscernible over ordinals. And the remark is that this is in some sense optimal, because Kondo's selection theorem says that every non-empty sigma 1,2 set has a delta 1,2 element. Notice we have here pi12. And Levy already showed that this is optimal, but Levy's example was not about a definable pair without definable elements. And that's what's new here. This paper with Conove has appeared in the archive and is under review right now. Now, in the interest of me stopping sometime within an hour, I'm going to skip this page because we can always come back to it, and start my anti-Leibnizian phase of the talk. Back when I was reading popular books on quantum mechanics, I remember seeing a quote that some people think this code actually wasn't made by Niels Bohr, but I found a reference where his son actually says that my father said exactly this, that there are two sorts of truths: profound truths recognized by the fact that the opposite is also a profound truth, in contrast to trivialities where opposites are obviously absurd. Okay, so it's obviously a philosophical point that one can easily argue with, but of course the catchphrase here is opposite. So what is the opposite of Leibniz's principle of identity of indiscernibles? I mean, it was already hard enough formulating the principle itself, meaning it wasn't until Michowski had this formulation that seemed to catch the spirit of the principle. So how do you negate it? Well, the lazy way is just to negate LM, but that's not sufficiently, I think, opposing. you need a more dramatic opposing. You could, instead of saying to oppose the existence of a pair of indiscernibles, you could say there are incredibly many of them. And in set theory, we say that by saying there are class many. And you could also fine-tune or strengthen your notion of indiscernibility to order indiscernibility. Not just one element at a time, but many elements at a time. Basically, they're indiscernible in the sense of order indiscernibility. So how do we formulate this? Okay, there are many ways of formulating this, and there are different flavors of these theories. So I'm not at all suggesting that what I'm showing you is the end of the game, is in a way the beginning of the game. The easiest way to formulate, and the cleanest, I would say, is to add a predicate, a fresh predicate, I of x, unary predicate to set theory. And consider the following axioms. Stick with set theory, ZFC, and then add instances of replacement in this extended language. So you really are taking I seriously now. You're saying it can participate in set theoretical reasoning. And it's easy enough, instead of just saying it's a class, you might as well take a class of ordinals. It's a cofinal class of ordinals. It's pretty easy to see that if you have a class that is indiscernible, then the ranks are order indiscernible and they're ordinals. So this is not much of a restriction. So that can be obviously added as a statement. And then you can add a scheme which says, but the scheme says that for any n-ary formula, this statement, which you're looking at, holds. So this is a statement involving I, because it quantifies elements of I here. So this is order indiscernible in the sense of Aramford and Mostovsky. Okay, so here's a theory, and we could say, nice. What can you do with this theory? What does it say about set theory as we know it? Just as a way of just testing the water, so to speak, some quick observations. You could quickly see that this is, you could build such models for this theory. If you pick a Ramsey cardinal, then V kappa expands to a model of ZFCI. It's a one-line proof. Just enumerate formulas of set theory so that the nth formula has, let's say, exactly n variables, and define this partition F from finite subsets of kappa to 0 and 1, depending on basically whether phi sub n holds for that set that you picked. So this is one can say it's a light face. If V kappa satisfies a light face version of being Ramsey, then it expands to ZFCI. If there's an uncountable well-founded model,
the other direction? Is it true the other direction? I mean, is that a characterization of Ramsey, or I guess maybe
yes. If you allow, not the light face, but the bold face version. If you allow arbitrary subsets here, and you say V kappa epsilon comma x has always indiscernibles, then yes, then you get Ramsey. And then something which takes a more fine-tuned result to prove is that if you have an uncountable well-founded model of ZFCI, then O sharp exists. And this has to do with the theorem, well, you quote the theorem of Silver, that if there's a limit lambda such that L lambda has an uncountable set of indiscernibles, then O sharp exists. So this is definitely strengthening of the usual formulation of O sharp, which has stronger hypotheses than just exactly what you're seeing here. But it turns out ZFCI plus V equals to L is consistent. So this is where the first sign that, oh, something fishy is happening. On one hand, the well-founded models basically are strongly saying V is not equal to L, but the theory itself is consistent. And I'm going to outline the proof of its consistency. Well, here's a variation of upping the ante, saying how even a stronger system than ZFCI, overtly stronger system, where you say not only there are indiscernibles over the universe, but you could iterate this process. You could add a sequence of subsets symbols I sub n, like the nth set of indiscernibles, such that you still have replacement in this extended language with this countably many new predicates. Each one is a cofinal subclass of ordinals. The first one is a class of indiscernibles for V epsilon. This is already a scheme, right, which is ZFCI. And then you could also add a scheme that the next one is a class of indiscernibles for the previous I's. So they're indiscernible. The ones in IN plus 1 are indiscernible even if you use predicates I0 through IN. You can see how fun this process becomes. You become very ambitious. Again, a Ramsey cardinal gives you consistency of this theory pretty much with the same reasoning as before. So I'm calling this now question L. When it comes to first order consequences of ZFCI and this super duper theory, what does it know about set theory? What kind of theorems of epsilon set theory shows? Theorems that we can understand, not just involving these abstract indiscernibles. Before I answer that, let me just point out that if you weaken amenability of I to separation, then you get a conservative extension. And this is, I won't go through the proof quickly, but it's just using the reflection theorem and Ramsey's theorem. And also if you formulate a weaker version which says there are arbitrarily large sets of indiscernibles, instead of saying there's one proper class of them, then again, you have conservativity. This one uses Erdo-Schrader. And here's the answer to question L. Question L was basically what are the first order consequences of these theories with indiscernibles. So if you give me a completion of ZF, then that completion of ZF expands to a model of ZFCI, if and only if it expands to this stronger theory. So it's only seemingly stronger. So this was a bit of a surprise for me. And that's equivalent for T expanding to a model of Gödel-Bernays set theory with a class global choice and the statement that order is weakly compact. So order is weakly compact. There are different formulations of this in class set theory. The formulation I have in mind is every ordinal tree has a branch, or equivalently, ord in the Erdős notation, ord arrows, ord 2-2. The usual kappa arrows, kappa 2-2 definition. These are equivalent in this setting. And now this answers the question. This part D finally answers the question. T is a completion of ZFC plus lambda. This capital lambda is in honor of Azriel Levy. And lambda,
Ali, I have a question, because the way the way you stated the theorem in words is stronger than what you wrote. Because you said if you give me a model and it expands, then it also expands to the stronger theory. But you're just saying that some model expands in the statement. So is it a model by model equivalence, or is it just that maybe you have to...
it's a model by model. Yeah. So
okay.
So I could have said every recursively saturated model of ZFCI. Sorry, every recursively saturated model of any, how about, let me rephrase it. If you look at this theory, which is now a first order theory, because you just have a bunch of n monocardinals that are incorrect. You take any recursively saturated model of ZFCI, it will also expand to ZFCI omega, it will also expand to GBC plus order is weakly compact. So it is, yeah, the model, it's, if you, I'm not sure if I answered your question or not. I think you're wondering if I have a model of, a particular model that expands to ZFCI, does it expand to ZFCI omega? Not necessarily. Yeah. Yeah, let me just pause on this for a second. This lambda, this Levy scheme is a bunch of statements. So it's a scheme which says for each concrete natural number n, that there's an n monocardinal such that V kappa is a signal n elementary submodel of the universe. So I'm going to give you just a flavor of what's involved in the proof. One of them is that if a model of set theory expands to GBC plus orders weakly compact, then the model satisfies lambda. This should not be too surprising because we already expect the ordinal being weakly compact to have all kinds of large cardinal consequences about the universe. It's really the next part which is surprising, that if you give me a completion of ZFC plus lambda, it has a countable model which expands to GBC plus orders weakly compact. So at the first order level, remember GBC doesn't have, for example, induction for statements quantifying over classes. GBC is well known to be, in some sense, a strong theory, in some sense, a weak theory. It's kind of a Spartan theory. And it turns out the most you can milk from GBC plus orders weakly compact is lambda, and exactly lambda. So that's the point of putting 1 and 2 together. So part 3 is a consequence of part 1 and 2. And then here's another theorem which connects these indiscernibles in a way with how you get the job done. If you have an automorphism of a model of a very weak fragment of ZFC plus delta, triangle is a global well ordering. And you take the fixed point set of J. So you have an automorphism of a model of set theory. You take the fixed point set of it, and you look at this fancy X consisting of subsets of M that are coded in N, meaning there are elements M in M such that the bigger model thinks that M is a member of A, where A is some element of M. So there are traces of elements of N on M. Okay. This is the family X. It's like a standard system. If M is an initial segment of N in the sense of that triangle, then you have a model of GBC plus orders weakly compact. This theorem is one of the places I would say there was no way I would have been able to find this theorem had I not been studying and working on models of arithmetic, because it turns out an analog of this theorem is true for arithmetic, where you get, if M is an initial segment, if the fixed point set of a particular automorphism initial segment, that particular initial segment is a strong cut, whatever that means. It's a concept in models of arithmetic. And it turns out strong cuts in models of set theory buy you GBC plus orders weakly compact. In models of arithmetic, they buy you ACA 0. So that's the analogy, ACA 0 and GBC plus orders weakly compact. I'm cognizant of time. Is it okay if I finish in a few minutes, Joel? Okay.
We have plenty of time, so please go ahead. Yeah.
Another theorem which is very helpful in proving this equivalence that we're looking at, Theorem L, is that if you take a model of basically ZFCI, but you also have a global well ordering at work. So the indiscernibles are indiscernible not only over epsilon but also over this global well ordering. So you can imagine, for example, N being a model of V equals to hot. And if you take an element, and if you take a particular model of this theory where every point in M is definable from elements in I, in other words, the model M is the atomic model of the theory, or in other words, is the Skolem Hall of I under definable Skolem functions. So M is a tight model. Everything is definable from elements in I. Then if you consider this linear order, which is gotten by attaching Z to the end of I, and then stretching the indiscernibles to I, from I to I star, then this bigger model admits an automorphism whose fixed point set is precisely M. So this is exactly where we hook up to the previous page, and we buy M satisfying lambda, or an expansion of M satisfying GBC plus orders weakly compact. And then finally, this theorem which is, now this theorem is about GBC plus orders weakly compact. It tells you how much power it has, even though we have limited capacities at work because of GBC, would not be able to quantify over classes. If you give me any class in the collection of classes of this GBC model, there's another class that codes an elementary end extension of m comma x with the least new ordinal. So you could elementary end extend the universe in GBC plus orders weakly compact with the least new ordinal. And the consequence of that is that it allows you to get hold of an element in your set of classes that is a satisfaction relation of mx. I think this would make more sense if I just finish with this last page, which is, let me blow it up a little bit. Just to give you a flavor of the argument, and this is my last page. So, and it tells you also how non-standard models are being used. So suppose you have a model m comma fancy x of GBC plus ORD arrows ORD 2 2. Then by the usual proof that kappa arrowing kappa 2 2 gives you a more general version where 2 and 2 can be replaced by concrete integers m and n, you get this super duper version. Notice m and n are meta-theoretic natural numbers. These m and n are not necessarily in the model arbitrary natural numbers of m, because m might be having all kinds of non-standard natural numbers. So this is just quantification in the meta theory. And then by compactness, by replacing mx by an elementary extension of itself, you can get hold of a non-standard integer such that ORD arrows ORD super C sub 2 to the C for some non-standard C. So I'm just replacing m comma fancy x with an elementary extension of it. That's all I'm doing here by the time I'm going to star. Now, once you have this statement, this ORD arrows ORD C to C, then imagine, now come to the right-hand side of this diagram, to this picture. Here's the model M of GBC plus ORD is weakly compact. And this is the family of subsets, this cloud of subsets of M. Using the theorem on the previous slide, I know there is an elementary end extension M star in the family X with the least new ordinal gamma. So this is where I'm using that previous theorem. And now because M star is an elementary end extension, it can compute the theory of gamma with constants from V of gamma. And we can be assured that this theory, which has all kinds of non-standard sentences in it, would be a member of our family of classes. So this is getting hold of a satisfaction class, S in the family of classes, which might give you gobbledygook for non-standard formulas, but for standard formulas, it exactly gives you the elementary diagram of M. And then we just sit down and just enjoy a very soft argument. In M comma S, we define a function from subsets of ordinals of size C to the set of, think of 2 to the C as a set of all 0, 1 sequences of length C. And the function is given by, you give me an alpha, which is the sequence of length C. I look at the truth value of phi sub I of alpha. It's either 0 or 1, according to this satisfaction for I less than C. So I'm getting a member of 2 to the C. And then using star, therefore I have a homogeneous subset of size ordinals. And that's my desired set of indiscernibles. So that's pretty much gives you a flavor of this last step of the proof. And that being my last slide, let me just officially announce it and thank you for your patience.
Well, thank you very much, Ali.
Yeah.
So that was really great and fascinating.
Yeah.
Are there any questions? So I can't really see everyone, but if you want to ask a question, then just feel free. Oh, Neil Barton has a question.
Okay.
Thanks very much. That was really, really interesting. So you've primarily looked at first order theories, either two sorted first order or first order theories, possibly with parameters. Do you know how these results generalize when we look at these semantic extensions of ZFC? So we either let ZFC be formulated in weak second order logic or quasi weak second order logic, or one of these extensions where we get a bit more expressive power?
The variation I've looked at is if you look at the Leibniz-Minkowski principle, which says that if you give me two distinct objects in the universe, I'll distinguish them if I go to a V alpha by some first order formula. If you change first order to a formula in some logic, for example, second order logic or some infinitary logic, some logic with extra quantifiers.
Right.
So it turns out as long as your logic is well behaved, and pretty much most infinitary logics or logics with extra quantifiers or high order logics are well behaved in the sense I have in mind, then it turns out you get still LM back. So
cool.
To be a stronger version actually gives you just LM back. But other than that, I haven't looked at indiscernibility. So basically what I just mentioned was if you tinker with LM, and, play with that. And I think the main reason I haven't looked at that is because anything away from first order logic for me when it comes to dealing with models of set theory is extremely unmanageable. And I don't know the model theory. The model theory is really wild, I should say.
Yeah, right. Yeah. Cool, thanks.
So I have a couple of questions. So, okay, you sold us LM as a version of Leibniz principle.
Yes.
And then you sold us ZFCI as the opposite of that. I mean, as but then you said that you can get ZFCI in a model of V equal L, which of course has V equal HOD and therefore has LM also. And so that's a model then in which you have both the Leibniz principle and the anti-Leibniz principle happening.
Jill, you're absolutely right. And this is it's a point where the only answer I have to you is pretty much the complementarity principle in physics. So in a way, maybe instead of thinking of them as opposites in the sense of not coexisting, as basically honing in on particular aspects of reality, and overtly these aspects might be contradictory, but they could coexist. So going back to exactly the point you made, of course, one could say, well, the models of ZFCI, where V equals to L holds, are not real models because they're not well founded. But at the first order level, of course, we have consistency and all as well.
I see. So, but maybe it isn't another way of looking at it that, look, the LM is giving us Leibniz principle, except it's basically modding out by ordinals. It's allowing free ordinal parameters somehow, right? Because you're saying two sets are distinguishable if they're, I mean, it's saying you have to pick an alpha where they're distinguishable in that alpha. It's like using alpha as a parameter. And so, yes. But ZFCI is all about the indiscernibility of the ordinals themselves. Of course, if you allowed ordinals as parameters, then they would be discernible from each other that way. I mean, and so, do you understand what I'm saying?
Yeah. I think what sells the LM as a basically capturing Leibniz's is the fact that if you have LM, I mean, forgetting those parameters that you mentioned in the class of in the model, you would be assured to be able to build a model with no indiscernibles. And conversely, if there's a model where there are no indiscernibles, LM holds. So overtly, that theorem in a way tells you that you can kind of get away with these ordinal parameters. Of course, what's really at work in the proof are those ordinal parameters in the reflection theorem. So maybe one interesting question would be to prove that, let's say for Zermello set theory or for ZFC without power set, there is no first order condition that works for these theories what LM does for ZF. So I think something very special is happening in ZF, which in a way gives all the power that it does to LM.
So if anyone else has a question, please just mention it in the chat or jump in. Meanwhile, I have another, oh my gosh, what happened?
Can I jump in?
Yes, please.
So this is motivated by the Silver-like theorem that if you have these indiscernibles, then you get O-sharp, provided you've got a sufficiently good model.
Yes.
Along the way from indiscernibles to zero-sharp, Silver had remarkable indiscernibles, in particular that the indiscernibles are not only a proper class, but a club, if you choose properly. Is there anything like that for ZFCI?
Yes. Yeah, actually, I mentioned there are various variations of ZFCI that I just showed you some of them. And one is exactly where you add that I, the class of indiscernibles, is a club. And there, if you look at that theory, its first order consequences are ZFC, but plus for each concrete natural number n, there is an n subtle cardinal kappa, such that V kappa is an n elementary submodel of the universe. So if you replace n modular by n subtle, then you get remarkable indiscernibles that way. A question that I don't know the answer to is if we soup up remarkability to being a diagonal set of indiscernibles, in the sense that if you have let's say alpha and beta and gamma, where alpha is less than beta, less than gamma, if you have three ordinals that are in this set of indiscernibles, then the beta and gamma are actually indiscernible over any parameters below V of alpha. So this would be often called the diagonal indiscernibles in arithmetic. And O-sharp has this property. And I don't know what happens if you add this stronger version. You might be able to get GBC plus not only orders weakly compact, but some higher aspect of being a large cardinal. Yeah.
Thank you.
Yeah, sure.
So let me ask another question. So in the large cardinal context, I'm used to the technique of building models with indiscernibles by iterating an ultra power. Like if you have a measurable cardinal, you can iterate it out of the universe, and then the vapor trail that it leaves behind, I mean, the critical sequence is a class of indiscernibles for the model that's left. And there's many versions of this kind of argument happening.
Yes.
But that's not really how you were building your models with indiscernibles, by iterating ultra power. So I wanted to know.
Yeah, it's interesting because those indiscernibles that are born in the iterated ultra power formation are not amenable in general to the model for which they're indiscernible for.
Ah,
so
right.
I think
So it would completely break it. I see.
Yeah. So,
okay.
so that was kind of a
right. Okay. Yeah.
strange situation.
Right.
Yeah.
So I'm not seeing any more questions in the chat, so I'm going to ask another one.
Okay.
Okay, I was very surprised to see that you said that it's open whether in ZFC we can separate LM from V equal Hod. Did I understand that correctly?
Yes, that's right. Yeah.
So, okay, so it seems like the most important question to answer about LM is exactly that. If it's equivalent to V equal Hod, then that's going to say quite a lot.
Yes, I mean, it really shouldn't be, should it? I mean, it somehow,
what are your thoughts? So you expect a separation, and do you have any ideas on how we might prove
No, actually, I think any idea that I had didn't work. Meaning, I guess my first idea was the Sachs model, and then another idea was some version of this product of Jensen forcing that is used in Solovey's proof. But that in that version, actually, LM fails also. So there is no, as far as I know, no natural notion of forcing that has arisen as a candidate, and I think that's why it would be a very nice problem for people to work on, because it's of course it's an area of independence which we're looking at class forcing, but of course the technology is highly refined these days. So I have a feeling that the technologies is there. It's a question of connecting the right dots.
Right, I see.
Yeah.
So I see Corey Switzer has a question, so go ahead,
Okay.
Corey.
Yeah, I just wanted to know these Aleph-1 like Leibnizian models that you construct in the first part of the talk. Obviously, they're not recursively saturated, so they don't have a satisfaction class. But can they have an undefinable class, or are they necessarily rather classless?
Let's see. I haven't thought about that, and yeah, because the construction is gonna, the only way to maintain. No, I guess I don't know the answer to that question. So just to maybe rephrase it, is there an Aleph-1 like Leibnizian model which expands to a satisfaction class? Would be, I guess, one version of your question, right?
Yeah, I mean, or just an undefinable class in general, right? Even if it's not a satisfaction class. I mean, because the satisfaction class, doesn't that give you with non-standard?
That's right. It gives you recursive saturation. Yeah,
and you don't have
yeah.
that, right? Obviously, but you could still maybe have some sort of undefinable class. Like, I mean, conversely, maybe I'm wrong, but I imagine that probably the construction you give this omega-1 like construction, you could weave into it the kind of Kaufman arguments to make it rather classless. But I guess the question is whether it's necessarily rather classless.
Yes, I think your guess is correct about using Diamond to build a Kaufman model, but yeah. So I just overtly from the definitions involved, I cannot right away see why you should have that undefinable class. I'll write a note to myself to think more about that and get back to you on that.
All right, thank you.
So Neil Barton has another question.
I mean, it's sort of tangentially related, which is that there's this result from Steve Vickers and Philip Welch that if ordered is Ramsey, then there's an elementary embedding from an inner model to V, and that can't be definable. So I mean, I don't know if there's anything in that direction, although obviously Ord being Ramsey is a lot stronger than what you've looked at here.
Yeah, the theory I'm looking at, because it has only GBC as opposed to Kelly-Morse, it has amazingly, I would say, little power. I mean, in some sense, you can formulate orders even measurable by adding a predicate to the language of class theory, and look at the GBC version of that. And it turns out actually even if you say you have such a predicate and that predicate behaves like a kappa complete ultrafilter, that you still get the same first order consequences as order is weakly compact in the GBC context. So I'm just in one point saying it's a very bizarre universe, because we're used as set theorists to have lots of induction around and
right.
All kinds of constructions, transfinite constructions, and in the GBC context, even we don't even have induction for natural numbers, let alone transfinite induction. So going back to your question, I think I haven't seen any work on GBC plus Ordis Ramsey.
I think you get a satisfaction class out of the indiscernibles in that case, though.
Oh, interesting you said that, because I now remember having a discussion with Kentaro Fujimoto, and so it turns out you already get satisfaction from order being weakly compact. So that was, in a way, it was the last theorem that I mentioned.
Right.
But you're right. I think if you just have orders is Ramsey, then it's much easier to get a satisfaction class.
Right.
You need to work harder with a weakly compact assumption. Yeah.
Well, all right. Are there any other questions? Otherwise, I guess I'd like to thank Ali for giving such a great talk, and it's such a pleasure to have you here. And we'll be wrapping it up now. And the next meeting of the Oxford Set Theory Seminar will be in 2 weeks, and we'll have Philip Schlicht from Bristol speaking. And so please come back in 2 weeks. So.
And thank you very much, Joe. I also very much appreciate being invited to give a talk at your seminar, and to have such a distinguished audience listening to my nonsense. Okay. See you in 2 weeks.
Okay, thank you so much. Goodbye, everyone.